Okay, this is the video for the lesson 1.4 supplement. Hopefully you've done all the other pages, and this will be somewhat of a review. But I'd like us to consider this lovely rational function here, f of x equals to x squared minus 9 over x minus 3. We know this function is defined for all values of x except for when... And if you said, yeah, we're supposed to look in the denominator and make sure that it can't equal 0, you are definitely correct. So this is true except when x is equal to 3, because I guess I should say when x equals to 3, because that of course gives the denominator being equal to 0, and therefore it makes it undefined. So my question to you is, what happens when x approaches the value of 4? Okay. And if you think about graphing it out, you can. If you visualize it, you can. If you can't, you just want to plug in numbers. Yeah, you definitely can. Remember, I'm using the word approaches, so really the notation we're using here is the limit as x approaches 4 of the function f of x. And most people will probably just plug in the number, so I'll do the same thing. And I think you get the value of 7. Cool. Now the question is, what happens to the value of f of x, that's the y value, as x approaches now 3? So if I were to do the same idea as above, notice I get 3 squared minus 9 over 3 minus 3. I get this lovely thing, 0 over 0, and you're like, what? What is that? We call this an indeterminate form. We'll deal with this in a bit, but right now 0 over 0 is don't say 1, okay? 0 over 0 is something we just don't know. So I guess plugging in doesn't really work when you're trying to plug in a non-permissible value. Hey, notice, right? 3, non-permissible value. So what I'd like us to do right now is actually go to your calculator, your graphing calculator. I'd like you to type in the function and try these different values of x. And I'd like you to plug in these values of x, which are close to 3, and let's see what y values you get. Grab your calculator. Let me clear some of this stuff. I always like to put brackets, so I bracket the numerator, and I also bracket the denominator. We'll press graph. You get the lovely graph. Ooh, hey, it looks like a straight line. And if I wanted to actually make a table of values, I'll just go to second function graph or table. It already has values in here, so if I want to plug them in myself, I can just type over it, I believe. Yep, 2.5, 2.9, 2.99, 3, 3.01, 3.1, and also 3.5. So bam, those are your values. I'm just going to copy them down. I hope you do the same. 5.5, I think this one was 5.9, 5.99, 3 was error, which makes sense because that's what we set up top. 6.01, I believe, 6.1, 6.5. Okay, so the question is, what is the value of f of x, or y, as x approaches 3? I didn't say equal to 3, I said approaches, so getting closer and closer. You probably predicted, yes, it equals to 6. And so the calculus notation here is this: the limit as x approaches to 3 of the function f of x, this equals to 6. And I'll write this down in words once again: the limit as x approaches, I didn't say equal, remember, approaches 3 of the function f of x is 6. Good. So this brings us to the idea of these one-sided limits. If I look at that chart again, I was looking at getting closer to the value of 3 from the left side, so numbers that are a little bit smaller, or I can get closer to them from the right side. So I have notation for that as well. So the left-hand limit, okay, is written like this: the limit as x approaches to 3 from the left, which is a minus sign, so 3 minus of the function. And in this case, the value is still getting closer to 6, right? 5.9, 5.99999. This is the idea of approaching from the left. And the right-hand limit, meaning approaching from the right-hand side, we use a plus sign. So 3 plus, and this still equals to 6. Now, for a limit to exist at a particular value, we need the left-hand limit to be equal to the right-hand limit. So the calculus notation for this statement is the following. Okay. The limit as x approaches to a number c from the left, that's the minus part, of the function f of x, has to equal the limit as x approaches to c from the right of the function f of x in order for the limit at c. So the limit as x approaches that actual value of c of f of x to exist. Okay. So back to our example up here. If we were to look at the graph again, you'll notice that the graph looks like a straight line. So this graph is really a straight line, but what in particular happens at 3? Yeah, there is a hole or an open dot. But the limit at 3 works because the limit from the left and the right both approach the same particular y value, in this case 6. Okay. If they approach different values, then the limit at that particular value of 3 will not work. Okay, so here's some graphs I gave you. Let's take a look at trying to find the following limits. If I have the limit of f of x times g of x, we can actually split that up into 2 separate limits. So you can just calculate limit of f of x approaching 2, or as x approaches to 2, and g of x, and we just multiply those together. At 2 for f of x, it looks like the value of, oh, don't say 1, that's not the limit value. Remember, getting closer and closer. There should be 2. And if we look at the g function over here at 2, oh yeah, that's definitely just the value. It's 0. 2 times 0, last time I checked, is 0. Okay. Looking at b here, for limit with a division, we can just apply the limit to the top and also the limit to the bottom. That 2 there I can actually take out into the front. It's like a constant, you don't have to worry about it. You just have to multiply it back in afterwards. Interestingly enough, on the top, this is not g of x, but g of x minus 3. So you can either plug in the number or think about those transformations you learned in pre-calc 12. Oh yeah, all that stuff from pre-calc 12. This would be, what, shifting it left or right? Did you say right? Right 3 units, you could definitely do that. So you could just shift the graph right 3 units. 1, 2, 3, like this. Whee! Right? And then figure out at 1, it looks like the value is negative 2. Okay. Or you could just plug in 1 and just said, hey, what's g of 1 minus 3 or g of negative 2? And found that point there too. And then on the bottom we still have that 2, and the limit as x approaches to 1 of f of x, that's just the value of 1. So in this case, our answer is just negative 1. Cool. C. Just like A, we can split this up. What's that f of 2x represent? And if you remember from pre-calc 12, yeah, that's a horizontal compression by a factor of a half. The graph will look something like this. Whoop. And then at 1, it looks like the limit value here is still 2. G of negative x, that must be a reflection in the x or y axis. Do you remember? I believe this one is a reflection in the y axis. Is that correct? And so your graph will look something like this, reflecting it in the y axis. right? And I want the value at 1. So I believe this is just equal to 0. And once again, your answer here is just 0. Makes sense? Cool. Alright, turn the page. So to continue with this idea of limits, we often in calculus talk about something called continuity. And continuity can be defined in many ways, but one of the most basic ways of thinking about it is it's a continuous process. Gradually, but smoothly, it changes without interruptions. A lot of times that's kind of hard to understand, so think about it like this. If I could take a pencil and trace over the graph with one uninterrupted motion, so I don't have to lift up my pen and put it back down, or I don't have to do something weird to fill in the hole, then we know the function is continuous. So those are nice definitions, but we probably want to define it nicer with calculus concepts. So to do that, I'd like you to take a look at this little activity. I've given you this crazy function. I'd like you to find all these things first. Okay, and this should be a review from the page before. So I'm going to let you try it yourself, and then come back and check your answers before we move on to the questions. Go. Notice here the limit from the left and right are not the same, so the limit does not exist. DNE, does not exist. Does not exist. F of 0, though, is the y value at 0. That's that solid dot, so that's 2. And then we have here 3, 3. The limit then is the same, because the left limit and right limit are 3. F of 2 in this case, once again, with the actual solid dot, that's 2. So, I hope your answers are the same as mine. If it is, you have good understanding of limits. Next part here is the thing. What conditions are needed in order to make the graph continuous at both 0 and also at 2? So let's focus at 0. What's the problem here when I draw this? Yes, I have to lift up my pen. And so you've got a little jump here, and that's not good. So at x equals 0, or 4x equals 0, what do we need to do to make it exist? We need to make the left limit equal to the right limit. Or you can also say that the limit at 0 needs to exist. So it has to be some sort of number. Okay. Now what's the problem at 2? The problem here is that I had to lift up my pen and put that dot somewhere else and then draw the remaining. So the idea here at 2, I'll say 4x equals to 2, what you need is the limit exists, right? So the limit at 2 exists. We've got a number, but unfortunately it doesn't equal to the actual value. So this really has to equal to the value. So what we're saying is the limit must equal to the y value at x equals to 2. So, bottom line, in calculus, to define something as continuous at a certain point, it says a function is said to be continuous at a certain point c. Now once again, c is an x value, if the following conditions exist. F of c is defined, meaning there is a y value. There is a y value. The limit at c must exist. So when I approach to that value of c, the y value must also exist somehow. And the key thing after that, and star of this, is then the limit at c then must equal the value at c. And if you have these conditions, then you know it is continuous at a certain point. So in calculus, we don't really talk about continuity of the whole function. We talk about where it's continuous at a certain point. Because most of the times the functions are nice, except at some weird particular points, like where there's a hole or where there's a jump or an asymptote. And those are the places we're really trying to inquire whether it's continuous or not. So the last note for today, if I asked you about polynomials, okay, now think about polynomials learned in pre-calc 11 and 12 and all that kind of stuff. Polynomials are always, and I'll give you the answer, continuous. And the question I have for you is, can you explain why? So they are always continuous, and not just that, I'll say everywhere. So I'll let you think about this. Can you explain to yourself why all polynomials are continuous everywhere? All right. Thanks for watching. Do some work now.